Salam and welcome everyone. So today we're going to be working on the question on the screen that says, suppose that 6.0 millimole of perfect gas molecules initially occupied 52 centimeter cube at 298 kelvins and then expands exothermally to 122 centimeter cube. Calculate the change in G for this process. So of course, because we are dealing with a science based question or chemistry question, we're going to first of all write out all the parameters that we're given in order for us to determine what to do. So we're told the number of moles is just simply 6.0 millimole, or let's just say 6.0 times 10 raised to the power negative 3 mole, okay, of perfect gas molecules, okay, initially occupies 52 centimeter cube at 298 Kelvin. So we have an initial volume to be 52. Let me rewrite that. 52, okay, centimeter cubed, okay, at 298 Kelvin, and then expands isothermally. So we have the final volume to be 122 centimeter cubed. And then we're told that this is an isothermal question. So that means the temperature is constant throughout the entire process of expansion. And that value for temperature is 298 Kelvin. So calculate the change in G for the process. So we're asked to find the change in molar Gibbs energy. So the first thing you have to know is when you're dealing with an isothermal expansion problem, you have this formula. You have the change in G, okay, of M. This is what I have of the final pressure, okay, equal to the change in G of the initial pressure, okay, times RT, plus, I apologize, not times, plus RT ln P final divided by P initial. Now, the problem with this question is this. First of all, we're not giving any value for pressure, and we're also given a value which is just the change in G is what we're supposed to look for. We're not supposed to look for the change in molar Gibbs energy. So those are the two issues that we've come across. But since it's a perfect gas question, we can convert and find the initial pressure as well as the final pressure based on the parameters we have, right? For example, we have the initial volume, we have the temperature being constant, we have the number of moles. That means we can find the initial pressure. So this is the formula we're going to use, but we need to make sure we have all the proper values that is necessary for this question. So what we're going to be using is just the perfect gas law. So PV equals nRT is what we have. So that's just going to be PI, VI, the temperature, the gas constant, number of moles is constant. So that's actually just going to be P initial is equal to nRT divided by V initial. So this is it. But the issue we have is that we're given our answer in centimeter cube. Sorry, our initial volume in centimeter cube when we're supposed to actually have that in decimeter cube. So we're gonna have to convert from centimeter cube to decimeter cube because the gas constant we're going to be using is going to be in decimeter cube. So we're going to go from centimeter cube to decimeter cube. So we know generally, I know that I've been doing a lot. I promise you it's going to make sense. We know that one um decimeter is the same thing as 10 centimeter. So 1 decimeter cubed is going to be how many centimeter cubed? Sorry. It's going to be how many centimeter cube? I don't know what's up with the pen. So that would be 10 centimeter cubed, all of that. So that would be 1 decimeter cubed equals 10 times 10 times 10. That's 1,000 centimeter times centimeter times centimeter. That would be centimeter cubed. So you have that and you have the 52 centimeter cube, so that would be 52 centimeter cubed, so that would be equals to that. So that's just, let's just call this unknown x because of course we're trying to find what this value is. So we have 52 centimeter cubed, that's just going to be 1,000 centimeter cubed x equals 52 centimeter cubed times 1 decimeter cubed. So that would be times 1 decimeter cubed. So that would be x is just simply going to be 52 centimeter cubed decimeter cubed divided by 1,000 centimeter cubed. Of course, you cancel out the centimeter cubed, 52 divided by 1,000. So x is just simply going to be 52 times 10 raised to the power of negative 3 decimeter cubed. Applying this knowledge to the final volume, we can just say the initial volume first is going to just be 52 times 10 raised to the power negative 3 decimeter cubed. Applying this knowledge to the V final was just going to be V final is actually going to be 122 times 10 raised to the power of 3 decimeter cubed. So I think that this is, we get the point, right? So now that we have that, we can actually find our P initial. So yeah, we can find the P initial. Let's go into the next page. So P initial is equals to nRT V initial. This is a lot of work, I know. But that's the price you pay for learning. So that would be 0.08206, okay? DM cube ATM, okay, divided by mole Kelvin, okay, times R. Sorry. That's R times, I forgot the number of moles, so I'm just going to add that here. So number of moles is just simply 6.0 times 10 to the power negative 3 moles. So times 6.0 times 10 to the power negative 3 moles, okay, times the temperature. We have that to be 298 kelvins divided by the V initial, which we just converted. That would be 52 times 10 raised to the power negative 3 dm cubed. So 52 times 10 raised to the power negative 3 dm cubed. Of course, we cancel out dm cube, cancel out Kelvin, cancel out Kelvin, cancel out mole, cancel out mole. We have 6.0 times 10 raised to the power negative 3. We just cancel out the 10 raised to the power negative 3. Cancel that out. So what we actually have now, we're just going to input in the calculator. We have 0.08206 times 6 times 298 divided by 52. When you input that information in your calculator, we're going to end up getting 2.8216 atmospheres. And of course, we know from our combined gas law, anytime you have temperature constant, you have P initial, V initial equals P final, V final. So we're just going to basically find what's P final. So P final is just going to be P initial, V initial divided by V final. So that'll be P initial is just going to be 2.8216 atmospheres times V initial. We know that to be 52 times 10 raised to the power negative 3 dm cubed. So that would be 52 times 10 raised to the power negative 3 dm cubed divided by V final, which is just simply 122 times 10 raised to the power negative 3 dm cubed. Okay, when you cancel out the dm cube, cancel out dm cube negative 10 raised to the power negative 3 times 10 raised to the power negative 3, that will be 2.8216 atmospheres times 52 divided by 122. You're going to have the P final to become 1.2026 atmospheres. Yep, that's how it's done. So that's the P final. So now we have that. Now we can properly substitute, right? Let's remember that we got this formula here. So GMP, the molar Gibbs energy of final pressure, okay, equals to the molar Gibbs energy for the initial pressure plus RT ln P final divided by P initial. So that would be change in the molar Gibbs energy, because I'm actually going to have to put GMPF minus GMPI. So the final minus the initial will just give you the change in molar Gibbs energy equals RT ln P final divided by P initial, right? So that's how it's done. But then we have one issue. The issue we have is that we're not asked to find the molar Gibbs energy. We're not asked to find the change in molar Gibbs energy. We're asked to find just the change in Gibbs energy. So note this, okay? The molar Gibbs energy, okay? The molar Gibbs energy generally is just the Gibbs energy divided by the number of moles. You would get the change in molar Gibbs energy. So what this is telling you is this: for you to be able to get the change in Gibbs energy, you're going to have to cross multiply, and you have the change in Gibbs energy is actually going to be the number of moles times the change in molar Gibbs energy. So what you're going to do is you're going to times this equation right here. Let me call this equation 1. You're going to multiply this equation 1 by the number of moles. So let me write this here. Multiply, this is a lot, equation 1, okay, by number of moles. You're now actually gonna get the change in Gibbs energy, which is what you're actually solving for. So when we multiply equation 1 or equation I by n, which end up with n change in GM, okay, equals nRT Okay, ln P final divided by P initial. So rewriting this is just going to be the change in Gibbs energy equals nRT ln P final divided by P initial. So the change in Gibbs energy is just going to be N number of moles. Let's go back to our question. The number of moles is 6.0 times 10 to the power negative 3 mole. So that would be, let me write it in a different color, 6.0 times 10 to the power negative 3 mole. Okay. Times R. We're going to be using the gas constant 8.3 145 joule per mole Kelvin, mainly because our units for any energy related value is going to be in joules. So Gibbs energy has to have the units joules. So we're going to be using this gas constant times temperature, which we know to be 298 kelvins according to the question. So 298 Kelvin here, and all of that times ln P final. We just solve for that. P final is this one right here, 1.2026. So 1.2026 atmospheres actually. Okay. Divided by, what's this called? The P initial, which is 2.8216. Divided by 2.8216 atmospheres. And I know some of you may be wondering, why didn't we convert from atmosphere to kilopascal? Well, because we're going to be like canceling out the atmospheres anyway in a question where we're just focusing on like it's ln into bracket the information with the pressure. It's not like we're multiplying pressure by another totally different value. We're just dividing between two pressures, so we can leave it at whatever units we want. So that's it. So we've canceled out the atmosphere. We're going to cancel out the mole. We're going to cancel out the Kelvin. As you're aware, since it gives energy, we're supposed to have an answer in joules. So the change in G, or the change in Gibbs energy, will be 6.0 times 10 raised to the power of negative 3 times 8.3145 joules times 298 times ln 1.2026 divided by 2.8216. So you're supposed to input all of this information in your calculator. But before we do that, let me break it down. Let's say 6.0 times 10 to the power negative 3 times 8.3145 joules times 298 Kelvin. Putting that in our calculator, we have 14.86633 joules. Okay, times ln 1.2026 divided by 2.8216 is just the same thing as 0.426212. So that's basically it. When you multiply them together, you end up with negative 12.6783 joules. That's basically the answer to this question. But then again, we are chemists and we need to make sure we put in the proper number of sig figs. So we have to go back to our questions to see how many significant figure is the lowest. So like when we look at our values, we're going to see the lowest number of sig figs and we're going to go with that. So we have two sig figs here, two sig figs here, three sig figs here, three sig figs here. So the lowest number of significant figures is simply two sig figs. So we're going to put our answer in two sig figs. So the change in Gibbs energy is just going to be negative 13 joules. So this is basically the answer that we're solving for. Like that's why we did this whole calculation. So hopefully this is easy for you guys. If you have any questions, please put it in the comment section. If you have any concerns, also put it in the comment section. I'm here for you. I want to quickly mention something that I saw online, and I think that will be absolutely necessary. Please do not click off this video. What I noticed online is that rather than using this equation where you would have the molar Gibbs energy, P final, P initial, all of that, whatever stuff. What happened was, since this is an isothermal question, we had situation where we know that P initial times V initial is equals to P final times V final. So what was done in the problem I saw online was P final divided by P initial was made separately, was written in terms of P final. Sorry. So this equation right here was written in terms of P final divided by P initial. And when you do that, what ends up happening is you have V initial divided by V final. Although I did not do this, use this, what was eventually done by this person was that they basically did a shortcut where they ended up having the change in G to become number of moles times R times T ln V initial divided by V final. So what happened is that they didn't even have to go through the process of converting and finding the initial pressure and the final pressure. They just did 52 centimeter cube divided by 122 centimeter cube, and they had that and they substituted that in here, okay, and then they just used the number of moles times the gas constant times temperature, and they got the negative 13 joules. So I want to give you guys a short classwork that you guys should actually do this. I believe you're going to be getting 13 joules, even though I didn't actually solve it. I rather use the information that we had, and basically use my knowledge of chemistry. This person also used the information they had and used the knowledge of chemistry. So if this ends up working out to negative 13 joules, please use it if you're dealing with a multiple choice question. But in a situation where you are given a theory question, your professor might actually require you to use my method. So just basically do what works for you. This works for me because I can clearly see whatever it is that I'm doing, because I know that the isothermal equation is actually what I wrote here. What this other person did is that he manipulated the equation in such a way to make the question easy to solve. So basically, do whatever works for you. I wish you guys all the very best. If you have any questions, please put in the comment section. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.